Hey guys, Mr. Backberg here. In this video, we're going to look at connecting differential and integral calculus. Now we're going to look at a little bit of an exploration where we find the derivative of an integral. So we've got this picture of some general f of x function on a closed interval from a to b. Now what we're going to do is choose any x value that's greater than a within this interval. So let's say we wanted to choose this x value right here in our picture. Now what we're going to do is look at finding the area underneath our curve between a and x. So if we think about finding the area of a whole bunch of slices of our picture, what we're going to do is we're finding these areas and then we're adding them together in order to figure out what that area would be underneath our curve. Now this is technically an accumulator function. We're finding all of these areas and adding them together. It's accumulating. I'm going to call that function capital F of x. And this accumulator function is the area underneath our curve. So we could also talk about that as being an integral. So this is an integral from a to x of our function. Now I can't use x in here because x is this value that I chose along my x-axis. So I'm going to introduce a new variable, and this is just a dummy variable. I'm going to use t, and because this is an integral, I'll have to put dt on the end. Now let's say we wanted to go one step further over from that x value. So I wanted to add one more slice in here. Then this extra area that we just added in here, I'm going to call delta capital F. That's the change in our accumulator function. But by going one step over, not only did we change the accumulator function, we also changed our x value. So however far we moved over this distance from our x value over to wherever our new value is, that change in the distance is the change in our x value. So I'm going to call that delta x. And then the height of this chunk that we just came up with in here on our function, that's our f of x value. Now if we think about this kind of rectangularly, then the area of this segment that we just added, that delta capital F area, if we think about it rectangularly, then the width of that rectangle is delta x times the height of that rectangle would be f of x. Now let's say we wanted to look at this accumulator function, this capital F of x, but we wanted to find its derivative. Going all the way back to the beginning of the year, we talked about derivatives as being a limit. So what we're going to do is take the limit as the change in our x value approaches 0. Now the actual derivative is the change in our function value divided by the change in the x value as that delta x is approaching 0. But as that width, as that delta x value gets closer and closer to 0, then we really just get closer and closer to that f of x value. So we can say that the derivative of our accumulator function, which is the same as our integral, so the derivative of that integral is really just equal to f of x, the function itself. Now this turns out to be a really important idea in integral calculus. The derivative with respect to x of the integral of some function f from a to x is just the function f itself. So we can see in here that we're doing the derivative of the integral of some f function from a to x, and the derivative of that integral is just the f of x function. So that means that this integral is the antiderivative of our function f. Now, just like it sounds, the antiderivative is the opposite of doing a derivative. So we can sort of think about integration as the opposite of differentiation. Now we're going to let capital F represent some antiderivative of our function f. So if we do the integral of our function f from a to x, then that's going to equal our antiderivative plus some constant value. And the reason why we have to add that constant value on the end is when we do a derivative of a function, If there's a constant value on the end of our function, then the differentiation really just turns that piece into 0. So when we do integration, we don't know if there was originally some constant value on the end, since it would have turned into 0. So we put this placeholder of c on the end to help us account for any potential constant that could have been in our original function. But now to figure out how we're actually going to calculate these definite integrals, what we're going to do in here is we're going to let this x value in our integral just equal a. So then really what we've got in here is our integral of our f of t function with our dt attached, and we're going from a to a. Now, since we're looking at x equaling a, then our antiderivative, capital F, we're going to have to look at that at a, since we let x equal a, but we've still got this constant value that we're adding on the end. Now, one property that we talked about with integrals was that if your upper and lower limit for the integral are exactly the same, then that integral value will always be 0. So we can say that 0 is equal to this capital F of a plus our constant c. Now, if we wanted to solve to figure out what this constant c value was, I would subtract this f of a over to the other side. So we would have negative f of a equaling our c value. So then what I can do with that is I can take this c value, or this negative f of a, and I can go all the way back up to my initial integral, and I can plug in that value there. So then on the end here, this would say capital F of x minus capital F of a. So what this all leads to then, in order to evaluate a definite integral, if we want to look at the integral of some f of x function from a to some x value, then what we're going to do is take the antiderivative at whatever our upper limit x value is, and we're going to subtract the antiderivative at whatever our lower limit a value is. This part right here is really, really important. This is how we're going to do our definite integrals. We're going to figure out what the antiderivative of our function is. We're going to plug in that upper limit of x. We're going to plug in that lower limit of a, and we'll do our antiderivative at x minus our antiderivative at a. Now, there are a lot of different integral rules. So here we've got a whole bunch of different rules for polynomials, and we've got a bunch of different rules for trig functions. There's rules for exponential and logarithmic functions. There's also rules for inverse trig functions. Now, all of these show up on your integral sheet that I gave you guys. So as we're doing our integration, if we see any of these common types of integrals showing up, then we can use these shortcuts. So in this example, we're going to look at finding an integral using antiderivatives. So we want to find the integral of the sine of x dx from 0 to pi using the formula that we talked about earlier. So the very first thing that we need to do is integrate this sine of x, or we need to find its antiderivative. If we look on our integral sheet, we'll see that the integral of the sine of x turns into negative cosine of x. So that's our first step. Find the antiderivative of whatever function it is that we're dealing with. Now, our formula says to take the antiderivative and plug in the x value, which is the upper limit of your integral, and then subtract the antiderivative at the a value, which is the lower limit of your integral. So I'm going to take this negative cosine of x, and first I'm going to plug in the pi. So this will be negative cosine of pi minus, now I'm going to do my antiderivative again, which is the negative cosine of x, but now instead of x, I need to plug in the lower limit for that integral. Now in the middle, this double negative is going to turn into addition. If we look at the cosine of pi, the cosine of pi is negative 1, but if we attach another negative to that, then that turns into positive 1. The cosine of 0 is 1, and we're supposed to add those together, so we get an answer of 2. Now looking at this example, we're going to find the integral of 4x dx from 2 to 5. Now before I go too far on this one, I'm going to use a property of integrals to take this 4 that's attached to the x and move it out to the front. So it's going to be 4 times the integral of x dx from 2 to 5. And now what we're going to have to do when we're integrating this x, there's actually kind of an anti-power rule that says if you're doing the integral of x being raised to some nth power, then as you do the antiderivative, what we're going to do is 1 over the n power that you started with, but we're going to add 1 to that, and then we're going to take our x, raise it to the nth power, but add 1 to that power as well. So in here, we're really dealing with x to the first power. So when I do that antiderivative, the first thing I want to do is 1 over the power that we started with, which is just 1, but I'm going to add 1 to that, and then I take my x, I leave the power on there, but then I add 1 to that power. So if we work on simplifying this down, this fraction is really going to turn into 1/2, and then if I add 1 to that power, that turns into x squared. Now I still have my 4 multiplier out in front, so now if I take 4 times that 1/2, then I really get 2x squared. Now I still need to use my formula, which says take your antiderivative, but plug in the upper limit. So first we're going to plug in the 5. So we're going to go 2 times 5 squared. Then we do a little subtraction, and now we take our antiderivative, but plug in the lower limit for the integral. So this will be 2 times 2 squared. Now going through and simplifying this down, 5 squared is 25, times 2 is 50, but then we have to subtract 2 squared is 4, times 2 is 8, so 50 minus 8 is 42. Now one more example in here. We're going to find the integral of 3x squared minus 4x plus 7 dx from -1 to 1, again using our formula. Now in here, because there's a bunch of things being added or subtracted, we've got a property of integrals that says that we can integrate each piece individually and then just do the appropriate operation between them. So that's what I'm going to work on doing. I'm going to integrate first the 3x squared. So I'm going to pull that 3 to the front, and then I'm going to do the integral of x squared. So similar to what we just talked about, we said to do this integral, we were going to take 1 over the power we were given, plus 1, and then we were going to take that x and then add 1 to that power, so that becomes an x cubed. Now this fraction, 1 over 2 plus 1, well that really turns into 1/3, and then if we multiply by this 3 out in front, then that's just going to turn into 1x cubed, and I don't need to put the 1 in front of that x cubed. I can just write it as x cubed. Now doing something similar with this second integral, I'm going to pull that 4 to the front, so this is really going to say minus 4 times the integral of x, and we just did this one, x to the first power, so I have the minus 4 in here. I take the 1 over the power we were given, but add 1 to it, and then x, add 1 to the power, so that turns into an x squared. So again, this fraction turns into 1/2, but I multiply by the minus 4, or the -4 in front of there, so then that really turns into a -2, and then I drop down my x squared on there as well. Now, we haven't done one like this before. When you're integrating a constant, the only thing you have to do there is add an x onto it. So when we integrate this 7, it really just turns into 7x. So I'm going to drop that all the way down here. So this polynomial right here is our antiderivative, x cubed minus 2x squared plus 7x. But now I need to take that function and plug in the upper value for my integral. So I'm going to do 1 cubed minus 2 times 1 squared plus 7 times 1. So I'm going to get an answer from that, but then I'm supposed to subtract that same antiderivative with the lower value plugged in. So then this will be -1 cubed minus 2 times -1 squared plus 7 times -1. Now let's start with this first one. 1 cubed is 1. 1 squared is 1 times -2 is -2. And then 7 times 1 is just 7. So 1 minus -2 is -1, plus 7 is 6, minus, now on the back end here, -1 cubed is -1, -1 squared is +1, times -2 is -2, and then 7 times -1 is -7. So -1 minus 2 is -3, minus 7 is -10. Now in here we're taking 6 minus -10, so that double negative will turn positive, and we'll get an answer of 16. That's going to be it for this video. Thanks for watching.